Hello students, in the previous lecture we looked at what ISA means, and we also touched upon the point that there are two different types of ISAs, RISC and CISC, and we looked at some basic differences among them. And I stopped the uh, lecture mentioning that we will be taking RISC-V as an example and studying further. So in this lecture we'll start with RISC-V. It was primarily developed by University of California, Berkeley as an open source ISA. Now it is managed by an independent organization, Riskfree Foundation is its name, and riskfree.org is the site. You can go and check about a lot of new things that are happening with the Riskfree ISA. Risk-V, the way it has been designed, it is quite uh, typical of many of the current day ISAs that we have. So studying it will make things very, very relevant to you with the current computing systems, right? And then similar to Risk-V, there are many other risk ISAs which are uh, primarily used in the embedded market. For example, the consumer electronics or network devices or storage. We are going to look at one storage example during the memory module, and any day-to-day things that we use like cameras and printers, etc. So all these use the RISC style ISAs to build their uh, the small chips that would be performing very, very well defined actions. We will in the theory look at the 64-bit version of RISC-V. I'm going to tell what 64 means in a while, and in the practice uh, that is in the lab, you're going to look at or work with the 32-bit version of RISC-V. So just to give a complete picture, I'm going to touch upon both. So in the process of understanding what ISA means, we took RISC-V as an example, and we will understand how RISC-V was designed by looking at various type of instructions that are part of it. Primarily, the instructions can be grouped into three. Like I mentioned in the previous class, they are arithmetic instructions, data transfer instructions, and control instructions. We'll start with the arithmetic instructions in this lecture. The arithmetic operations like add, multiply, subtract, divide, uh, logical operations like and or XOR, shift operations, left shift, right shifts, etc. All these are together grouped as arithmetic instructions. All of them have some similar formats. I'm going to start with the add and subtract instructions. We can generalize more or less the same points for all the remaining arithmetic instructions also. So the add and subtract instructions have three operands. As you know, operands are the data that we expect the operation to be performed on, right? So among the three operands, two of them are source operands, one is the destination. For example, the RISC-V add instruction can look something like this: add a comma b comma c, where a is the destination operand and b and c are source operands. So what this instruction uh, performs does is it adds the content of b and content of c and writes the result to a. Similarly, subtract also has similar similar format. It has one destination operand G here, and E and F are source operands in that order. So the value E minus F will be return to G. Like I mentioned, all the RISC-V arithmetic operations have this form where they have three operands, two source and one destination, and the destination uh, op, uh, operand is written first, mentioned first, like A here, and the two source operands follow that. And the in the format you also see the operation that needs to be performed. For example, here ADD represents addition, SUB represents subtraction. So these short forms ADD and SUB are called mnemonics. And for let's say multiplication, you would use MUL. For division, we would use DIV, etc. So these are called mnemonics. So the primary motivation for the RISC-V designers to make the format uniform is to have some regularity. So what does regularity bring in? It brings simplicity in the implementation. And when we say implementation, the hardware that would actually perform, that would actually understand these instructions and perform the operation that is given as part of the instruction will be simpler, right? Then as an add-on, you can say if the hardware is simpler or regular, we can achieve higher performance at a lower cost. And when we say cost, it is in terms of the latency, you can say, or area or power. Okay, so this is the first design principle of RISC-V. Simplicity favors regularity. Let's take an example. A typical C code that we want to look at would be something like this, where we have five variables. F is the, you can say, the destination variable. What F is assigned is G plus H minus I plus J, right? So if we want to write this into RISC-V code, it would, excuse me, look something like this. So we have an add, and we have added G and H and written into a temporary variable T0. Following that, we also, the second instruction is we have added I and J and written it into another temporary variable T1, and finally we subtract the value of T0 and T1 and write it into F. So together these three instructions will perform the operation that we have written as a single line in C. So we have used the variable names here like T0, T1, F, I, J, G, H, etc. So these we have kind of naturally taken from the C code that we saw. But at the assembly level, we have more restrictions on the variable names. We cannot randomly use any names and write the assembly code. It will not be recognized by the hardware. So accordingly, we have what's called as register operands. If you remember in the RISC definition, I've mentioned that in RISC ISAs, the arithmetic operations can be performed only on registers, right? So the values on which we want to perform an operation will be readily available in the registers, right? And the operation is performed and the value is written into another register which is interpreted as a destination. So the 64-bit version of RISC-V has 32 registers, and each register is of size 64 bits. So it can store 8 bytes of data or 8-byte value. The registers are primarily used to access the frequently used data so that we don't need to go to the slower memory. And in case of 64-bit, it would be called as a double word. That also means that 32-bit is the word size in the RISC-V. So a 64-bit register would contain two words or double word, right? So, and in RISC-V, the registers, these 32 registers are represented as x0 to x31. We are going to use these register names to perform all the operations. We are going to look at the examples as we go. Like I mentioned, 32-bit would be the word size. And if we are looking at the RISC-V 32-bit version, it has the same 32 registers, but their capacity is only 32 bits. Now, I'll pause here for a moment to explain what the implication of this 64-bit and 32-bit versions is. Now, when I say that I have built a processor following RISC-V 64-bit ISA, what it means is my hardware can perform, let's say, addition or subtraction, multiplication, etc. on 64-bit values. But when we say that I have built a hardware or processor for 32-bit RISC-V, it means that I can perform addition, subtraction, etc. on only 32 bits. So accordingly, the compiler for these RISC-V versions will be slightly different. Okay, now a question can come saying that how can I perform 64-bit multiplication using a 32-bit hardware? So there the compiler needs to do some extra job on splitting the values, or rather placing the values in the registers appropriately and generating the code so that eventually the 64-bit multiplication is realized. Okay, so that is the reason we have different compilers for different ISAs. So a short note on the number of registers over the years. You can see in this table, right? On the first column is the machine name. The second column is the number of general purpose registers that these machines have, and third column is the architecture style. For the moment you can ignore it, and fourth column is the year that this machine has come out, right? So if you observe the number of registers right from 1950 to currently 2010, and even you can say 2020, they did not increase so dramatically, right? So we started with one somewhere in 2000s, we have hit 128, but right now we are limiting ourselves to 32 or 64-bit registers only. So why is that? We all know that registers are the fastest memory locations, right? And if we have a bigger set of registers, it means that I can store a lot more data closer to the processor to access it. But what's the downside of large number of registers is the circuit to decode the register number and get the value, etc. All those will become bulkier. It means that they will be slower and will also burn more power. So this is the second design principle of RISC-V. Smaller is faster. So as an extension, the memory, we can have millions of data stored, but to access the memory, it takes hundreds of cycles, right? We can't afford that much latency just to perform a single add operation. Okay. So now with these register operands in mind, let's go back and look at how the arithmetic instructions would actually look like. Okay, before that, let's try to understand the 32 registers labeled x0 to x31. So x0 always stores 0. x1 is used to store the return address. x2 is used to store stack pointer. x3 for the global pointer. x4 for the thread pointer. x5, x6, x7 and x28, 29, 30, 31 are used as temporary registers, and x8 is used as frame pointer, and a few other registers x9 and x18 through x27 are also used as saved registers. X10 and X11 are primarily used as function arguments or to pass on the results across different functions. And X12 to X17 are also used for function arguments. So if we try to understand what each register can be used for, the value in X0 is always fixed with 0, right? And usage of X1 as a return address register is suggested by the RISC-V ISA, and usage of X2 as stack pointer is fixed. And of course, you can use X2 for some other different operation also, but in the process, we will lose the stack pointer. At this moment, you need not worry about these new terms called stack pointer, global pointer, etc. We are going to look at them in this module. My main intention to give you this information is some registers are used for some specific purpose. Some registers can be used for any uh, regular work. Okay. So X3, just like X2, is fixed. It will always store the global pointer, but you can use it for any regular purpose also if you don't want to have any global pointer with you. Same with X4 and X8 also. And the remaining registers, it is the suggested usage. Like I mentioned, the RISC-V ISA guidelines this usage. All the suggested ones, and apart from X0, all the other registers, all the remaining 31 registers can be used for any writing or reading any value. When we say that we have built a RISC-V compiler, we need to strictly adhere to these guidelines by RISC-V ISA. Okay. What it means is when we give a C program to our RISC-V compiler, it's going to generate the assembly code following these guidelines. Okay. Now in this module, you are going to write your own assembly code. If you want to strictly follow the guidelines, you should definitely follow these pointers. Okay. Now let's go back to our C code. F equals to G plus H minus I plus J. And let's assume the variables F, G, H, I, J are present in the registers X19, 20, 21, 22 and 23. Now if we look at the actual RISC-V code which was generated by using a RISC-V compiler, it would look something like this. We have the same instruction sequence, add and subtract, but you can see the operands have changed. Now we are using the registers as operands. We have used X5 and X6 as the previous in place of the temporary variables we used previously. The value of X20 is G, X21 is H, so we add them and write it into X5, and the value of I is in X22, we add it with J, which is in X23, and we write it in X6. These are the destination registers, and we are using that as temporary registers, and in the end we are going to subtract X6 from X5 and write the result in X19. That's what we assume, that the value the register X19 would represent variable F. Now we have looked at the simple add and subtract instructions which were working with two source registers and one destination register. Now what if I have one value readily available with me? Let's say I want to add 4 to a variable. How do I do it? Does RISC-V give us any flexibility in that? Yes, it does. The constant value can be part of the instruction itself. We need not store it in a register and retrieve it. Okay. So the specialized instruction for this is ADDI, add immediate. What we what this instruction does is the value in x22 is added with a constant value 4, and the resultant will be written into the destination register, which happens to be x22 here. These type of instructions are called immediate instructions, and the operand we give here is called immediate operand because the value is immediately available, readily available to us. So this again, such instructions are provided as part of the ASA to make the common case fast. So if you remember, the one of the great ideas was designed for common case, right? So why do these immediate operands be common case? So typically we use many small constants in our code. For example, incrementing a variable or decrementing the variable, etc. So if we want to perform an increment on x, we simply write x plus plus, but what it actually translates into is addi. Let's say x is present in a register x20, so x plus plus translates to addi x20 x21. Okay, like I mentioned, if the value of some operand is readily available in the instruction itself, we don't need to access the register file, or we don't need to access the memory. So it will speed up the instruction execution. So almost all the arithmetic instructions in Riskfree have the immediate variants of it, like ADD and ADDI. Okay. Now we saw how a small operation like a equal to b plus c was represented in Riskfree assembly, but eventually how does it get converted into the machine code is where the instruction encoding comes into the picture. Right, again the information about instruction encoding is given by the ISA itself. Instructions are encoded using a predefined mapping, you can say, and written into the machine code, which is basically a sequence of zeros and ones. This is called instruction encoding. In the Riskfree instructions, in the Riskfree ISA, instructions are encoded into 32-bit words. Right, like I said, in Riskfree a word is of size 32-bit, so each Riskfree instruction takes one word of space. Again, to make the instruction execution hardware simpler, this instruction width has been limited to 32 bits, right? And this will help us to speed up the encoding operations, also decoding the instructions and executing them. So again, the point about regularity. Now the Riskfree assembly code, right, that the assembler has generated is consumed by the assembler, which again is tailor made for one particular ISA. Here it's for Riskfree. It consumes this assembly code and generates the machine code by following this instruction encoding. That is the reason we have a tailor-made assembler for each different ISA. So let's look at some of the encodings. The first encoding that we see is R format, and the 32-bit would be encoded like this. So each of these boxes, here we have 1, 2, 3, 4, 5, 6, 7 boxes is called a field. So if we want to look at what each field represents, the first field is opcode, short form for operation code. The second field is RD, short for destination register, and it is taking 5 bits space. Why is it taking 5 bits? Because we have 32-bit 32 registers in RISC-V. Function 3 again is a 3-bit opcode. Excuse me. RS1 is register source 1, RS2 is register source 2, and just like register destination, we have 5 bits for each of them, and the remaining 7 bits again is used for additional opcode. Now the operation that we want to perform will be given by the opcode, function 3 and function 7. Okay, now in the R format, all the operands on this on which this operation is performed is given by the registers. That's the reason we kind of represent it as R format. We have RD, RS1 and RS2. So if we want to quickly look at an example and understand how the R format instruction would look like, so here I've reproduced the same encoding that we saw in the previous slide. So if we want to convert this assembly instruction add x9, x20, x21 into machine code using the instruction encoding given by RISC-V ISA, it would look something like this. So opcode, 7 bits of opcode is replaced by value 51, function 3 is replaced by value 0, and function 7 is replaced by value 0. So together this 51, 0 and 0 represents add, and these values will be given by the ISA. Now if we and the register destination here is x9, so 9 is written here, the source 1 is 20 and source 2 is 21. So if we convert them into the sequence of ones and zeros, 51 is represented as a 7-bit number here, 9 as a 5-bit number, 0 as 3-bit number, 20 and 21 as 5-bit numbers, and the final 0 as 7 bits. Now together, if we group them in nibbles, so 015A 04B3 is the hexadecimal representation of add x9, x20 and x21. Okay, so this is the machine code of this add operation. For immediate operands, where we saw the ADDI, one of the operand is immediately available in the instruction, we have a different encoding said as I format instructions. So here, similar to the earlier, we have 7 bits of opcode, destination register, function 3 of size 3 bits, source register of 5 bits, and instead of RS2 and function 7, we have a 12-bit immediate field. So this I format is for all the immediate and even the load instructions. At this moment, I did not explain what load instructions are. We are going to come back to it. Just limit ourselves to the immediate arithmetic variants. RS1 is the source register. Immediate is the immediate value that we add or subtract or do and or whatever we want to do. And RD is the destination register. So a quick point on the immediate value, it is always represented as a 2's complement sign extended number. Okay, so if we look at this R format and I format, it brings us to the third principle of RISC-V, which is good design demands good compromises. Now what is the compromise we are making here is we are limiting the immediate value to be 12 bits only, and because it's in 2's complement format, the range is minus 2 power 12, right, 2 power 11 to 2 power 11 minus 1, right? So that is the maximum range we can use. Means those are the maximum values that we can include in the immediate instructions. So why are we limiting the size and position of the immediate field? Is to make things regular again, right? So probably uh, we can club function 3 and make it 17 bits, or sorry, 15 bits, and or move the immediate field before the RS field, etc. All these will complicate the instruction decoding that we need to do at the hardware. So to make things uniform, we have limited the size and position of the immediate field. So let's look at the other arithmetic operations, which are logical operations. These instructions help us to perform some bitwise manipulations on the data. They are primarily used for extracting or inserting a group of bits into a word. Also, a combination of these operations can be used as masks. So here is a comprehensive list of different type of logical operations that RISC-V provides. So shift left is the instruction SLL, and the immediate variant is SLLI. Shift right is SRL, SRLI, and we have an arithmetic variant here, which is SRA, SRAI. Then we have a bitwise AND or XOR instructions or operations, which are given by AND or XOR. So all the basic logical operations fall into R format, and the remaining fall into the I format. So sorry, the immediate don't directly fall into the I format. My mistake. There is a small change, which is uh, the first four fields are same, but the last field, which was in immediate I format instructions, the immediate field was 12 bits, but here it's 6 bits followed by 6 bits of function 6. So the value in immediate field gives how many positions that we can shift, the value that is given in RS1. So the very first instruction is shift left logical. What it does is it will take the value in RS1, shift it to the left, and it will fill the vacant bit positions with zeros. Basically what it's doing is it's multiplying the value in RS1 with a value 2 power immediate um, 2 power the value given in the immediate field, right? And this resultant is written into the destination registers, RD. Similarly, we have shift right logical. The value in RS1 is shifted to the right, and in doing so we are actually dividing it with the value 2 power immediate, right? And arithmetic, we have a variant in shift right because we need to decide what to fill the vacant bit positions with. Yes, we are moving the value to the right, right? Let's say we moved the value by 3 bit positions. Now what do we need, what do we do with the 3 empty positions? Whether we fill it with zeros or we sign extend, that is determined whether we are using the shift right arithmetic where we are doing the sign extension, or if it is logical we fill it with zeros. Okay, now an interesting question that I would like to pose to you, all of you, is why is the immediate field restricted to 6 bits? Okay, think it over, and we can discuss it in during the live session. If you find an answer, you can put it in the classroom directly. Okay, moving on, the logical operations, and we have it is primarily used to mask few bits and uh, or select few bits and write zeros in the other bit positions. So it would look something like this, and x9 comma x10 and x11, just like the add ADDI versions, right? So x10 x11 are the source and x9 is the destination. The other logical operation is OR. It would look something like this: OR x9 comma x10 comma x11. And OR are the mnemonics for AND operation, OR operation respectively, right? We have an separate instruction that performs exclusive OR operation. So it would look something like this: x or x9 comma x10 comma x12. So x10 and x12 are the source and x9 is the destination. So with this XOR instruction, can we perform NOT operation? So again, I'll leave it to you. Think it over and we can discuss. Few other ALU instructions, which is SLT, set if less than. So it performs some interesting logic here. If we take an example, SLT x13 comma x12 comma x11, what this instruction does is it will compare the value in x12 with x11, and if it is less than, then x13 is written with a value 1, otherwise it is written with a value 0. The immediate variant is SLTI, which is short for set if less than immediate. Now instead of x11 we would have an immediate value. So the value in x12 is compared with the immediate value, right? And if it is less than, then 1 is written to x13, otherwise 0. And to compare unsigned versions of the values written in the registers, we have SLTU, which is set if less than unsigned. Okay, the value in x12 and is still compared with the value in x11, but now those values are treated as unsigned numbers. So if we simply use SLT, the values in x12 x11 will be interpreted as signed numbers, but in SLTU, sorry I missed here, in SLTU the values will be interpreted as unsigned numbers and the comparison is done. So we have an unsigned variant for the immediate version also, SLTIU. Okay, so the ones which are using register operands will obviously fall in the R format, and the ones which are using immediate operand will fall into the I format instructions, right? So with this I'm going to pause this lecture, and the reading assignment that I give you is to go through chapter 2 of the textbook Computer Organization and Design by Patterson and Hennessy, Risk-V edition. Go through the subsections 2.1 to through 2.6. Okay, and along with it we will also float the first lab assignment, and this is again for practice, right? We are going to use Venus simulator to do assembly programming. Venus is a 32-bit RISC-V simulator. It means that you'll be working with 32-bit RV32 ISA. The link is provided in the slide. Go ahead and open it and explore. In the lab assignment that we are going to share with you, a detailed description on how to use Venus, what all different features are there in it, all those will be explained clearly. Okay, so we are assuming that you are starting at ground level 0. We want you to closely follow each of those steps so that you will get enough confidence to write some complex assembly codes as we go. And if you have any queries, you can post it in the classroom, or we can have the discussion during the lab sessions. With that, I'll pause this lecture. In the next lecture, we are still going to continue with Risk-V. Thank you.